the YouTube now. And I will start recording now. Okay, good morning, everybody. Welcome again for this new colloquium at the Instituto de Astrofísica de Andalucía in Granada, in Spain. And today we will have the talk by Dr. Eugenia Skolnick from the School of Earth and Space Exploration in Arizona State University in USA. And she will talk about measuring the magnetic fields of exoplanets with star-planet interaction. Eugenia will be properly introduced by Anton Alberdi, our Institute Director. Please, Anton.
Hello, good morning to everybody. It is a pleasure to have today with us Eugenia Skolnick. She is Associate Director of the Interplanetary Initiative and Associate Professor of Astrophysics at Arizona State University in the School of Earth and Space Exploration. She is an expert on exoplanets and stars, including the Sun. She uses telescopes, both ground-based and in space, to answer questions involving stellar evolution, exoplanet magnetic fields, and planet habitability. She is the principal investigator of the NASA Sparks CubeSat mission. She is also the PI of UV Scope, a NASA MIDEX mission concept, and the PI of the Hubble Space Telescope's HAZMAT, Habitable Zones and M-dwarf Activity Across Time program. Dr. Skolnick is also a member of NASA Astrobiology Institute's Virtual Planetary Laboratory and is member of several science and technology advisory committees for NASA's upcoming space missions, as well as a panelist for the National Academy's Astronomy and Astrophysics 2020 Decadal Survey. She's author of more than 280 papers in peer-reviewed magazines, and today she will talk us about measuring the magnetic fields of the exoplanets with star-planet interactions. Thanks a lot, Eugenia, for your presence at our Severo Ochoa seminar program, and thanks for being so early for you in our seminar program, and the floor is yours. Thanks a lot.
Wonderful. Thank you for that introduction and also for the invitation to come speak with you. I'm sorry it has to be virtual, but hopefully I'll get to come out to Spain and we can all talk and work in person. So hi, everyone. Good morning, good afternoon, wherever you happen to be. I'm so pleased to be talking to you today about measuring the magnetic fields of exoplanets with star-planet interactions. This is work that I and my colleagues have been doing now for over 20 years. I started this as a PhD student at the University of British Columbia with my advisor, Gordon Walker. And here on the bottom right-hand side, you see the list of my close collaborators on this particular research topic. Now, because this is a virtual meeting and I know that it's difficult to listen to an hour of someone just speaking at you, I'm going to try to make this as interactive as possible. So there are a couple of spots before the end that I'm going to pause for questions. So just be prepared that if you have a question, the time will come up to very soon to ask it. And I'm happy for the conversation and the dialogue. And if I do not get through all my slides, that is okay. I will not be offended. I'd rather hear what you guys are interested in hearing about and talking about. Okay. All right, so let's take a step back into how people were thinking about magnetic fields in the early days of exoplanet hunting. In fact, what these titles of early papers show is that the magnetic fields of exoplanets were one of the original exoplanet hunting techniques, not so much for the interest of the magnetic field itself of the planet, but rather using it as a detection technique. So looking for radio emission akin to our Jupiter's strong radio emission, but in exoplanets. And so the very earliest one I could find was this internal memo from the Jet Propulsion Lab, where it discusses the feasibility of detecting planets beyond our solar system by taking, essentially what this paper does is takes Jupiter's magnetic field, puts it out at a few parsecs, and discusses the feasibility of doing so. Of course, if anyone is interested in this, this is not a published piece of work, but I do have the original. I have a PDF of the original. So if this is of interest to you to read the details of, just send me an email and I will forward it on to you. Also in 1977, there was also more papers on the search for Jupiters using radio, and in 1986 again. And after that, it seems to have gone quiet until very recently. Now that low frequency radio arrays are coming online, like LOFAR, are we reinvigorating this idea of looking for exoplanets through the radio again, but particularly looking for magnetic fields. So my research interests back when I started graduate school was actually looking for magnetic fields on known exoplanets. And that's what we did. So why measure magnetic fields on exoplanets? Why measure them, right? That's a good question in the first place, not just to find the magnetic fields. So first of all, magnetic fields, also which we refer to as B fields, B for magnetic field in our usual physics notation, it controls planet exteriors, right? So there's increasing evidence. Oh, I hear some noise there. There's increasing evidence of magnetic fields protecting the atmosphere of an exoplanet and of planets in our own stars, in our own solar system. So for instance, the idea is that because Mars does not have a strong magnetic field, that the solar wind could strip off its atmosphere, and that conversely, the Earth's magnetic field protects the Earth's atmosphere. And there's growing evidence, including from the MAVEN mission, that's saying that this is in fact true. There's also some theories saying that if the magnetic field is too strong, then it can enhance the stripping of a planetary atmosphere. And so there could be a balance as to what is the magnetic field strength that a planet would need in order for it to be truly protective, and then exceeding that could be, in fact, destructive. So it's a fundamental property of an exoplanet, and it's something we need to get a better handle on. Also, magnetic fields probe planetary interiors. Now, this is very hard to do on exoplanets, right? It's very hard to send seismographs, at the moment impossible, to send seismographs to understand or look for pulsations and other kinds of internal probes. And magnetic fields can really do this for us remotely. So for instance, in the Earth, we know that the Earth's magnetic field is generated by its liquid nickel iron core. And we also deduce that that the core, or the interior of Jupiter, is made of metallic hydrogen, based solely on its measurement of its strong magnetic field. So again, magnetic fields are both important to understand the exterior and the interior of exoplanets. And so this was really the motivation to go looking for magnetic fields long ago. To give you a sense of how long ago, when I was doing my PhD, my entire thesis is on 13 hot Jupiters, because in fact, there are only that many that we could do this experiment on back then. And now, of course, we have over 5,000 exoplanets. So really, there's a great opportunity to continue this work with more planets than we had when we first started. So what we decided to do was use hot Jupiters as a laboratory for exoplanetary magnetic fields, because if you take this image, right, of a solar eclipse, right, so beautiful. I put a hot Jupiter here to scale. Typically, they are about 10 stellar radii away, so they're very close to their host stars, and they're in fact streaming through the magnetospheres of the stars. So you could imagine that the magnetosphere of the planet could be interacting with the magnetosphere of the star in a way that is measurable. And what we're trying to do is measure these magnetic interactions through increased stellar activity. So the technique is not to use radio yet, but this technique is to look for classic stellar activity indicators. In our case, we started off with calcium-2, which is a chromospheric activity indicator in the optical part of the spectrum. And I'll show you those data soon, but that's the motivation. And why these hot Jupiters are so interesting is because they lie in the sub-alfvénic regime of the star. So this is where the magnetic fields of the star and the planet can interact, right? This is what I call the SPI zone, right? So in our own solar system, here, if you can see my mouse, here I'm plotting you the alphane Mach number, right, which is the ratio of the wind speed to the alphane speed, along with with distance of the planet in solar radii. So for our own solar system, the Earth up here is up in the is out here beyond the sub-alfvénic point, and Jupiter is also out there beyond it, but hot Jupiters lie down here, right, where you could imagine information now can be transferred back onto the star because the alphane speed is greater than the wind speed. And so this was the motivation. And in fact, this had already been shown in stars. So if you have two closely orbiting stars, there is a increased heating or an increased activity in the sub-binary point. And there are a few papers that show this, Pishkanov 1996, this one by coincides 2000, and we showed it as well for ER-Vol, which is two sun-like stars orbiting each other very closely. And you could see modulated with the orbital period hotspots on the subplanetary point. And so we were motivated to do this now with hot Jupiters, where the idea is that the activity that you see on the star is modulated by the orbital period, not by the stellar rotation. So of course, we often see star spots, right, and modulation in on the period of the rotation, right? That is precisely how we measure rotation periods on stars. But here we're looking for variability on the orbital period of the planet, and that's the big key here. So we started a campaign of optical spectroscopic monitoring. Primarily, this was done with the Canada-France-Hawaii telescope on Mauna Kea. And we went and we looked at several hot Jupiter systems. We looked at their stars with very high signal to noise spectra over many nights. And you want to see these tiny variations. Now, the signal to noise, for those of you who enjoy spectroscopy, was about signal to noise of 500 in the continuum per resolution element. And so, of course, that is really high. So you need very bright stars, you need a fairly sensitive telescope, and you want to do this at relatively high spectral resolution. So it's not the cheapest or the most efficient experiment as far as experiments go, because it requires so much monitoring. However, it's really important, right? Because these are fundamental properties of exoplanets. And so here's the first, just showing you some of the, I guess you could call it now, historic data. This is from our very first paper in 2003, showing the modulation of the calcium core. That's this little thing here, right? So you can see how the photospheric lines are very, very stable from night to night. Each of these curves is taken on a different night. But the little bit of variability on the star, which is an F8 dwarf star, is very obvious, right? And here's the residuals that we plot from night to night. So it is a whopping signal at the 1% level, okay? And very low and very high signal to noise provides this low range. Now, what we need to do, of course, as I said, is see if this actually maps to this planetary orbital period. And in fact, in this case, this was our first discovery of magnetic interactions or some sort of planet-induced activity, right? Because it phases with the orbit of the planet and not the rotation period. So the rotation period is 7 days for the star, and the orbital period is 3.1 days. This particular system has a hot Jupiter, a Jupiter mass planet at 0.04 AU, and a minimum mass of 1 Jupiter mass. And here I'm just showing different points from different runs. There's 3 different runs from my team and 3 different runs from another team, Goodmere et al. 2012. And you can see that they do phase fairly well with the orbital period at very high significance. Another thing to point out is that this phase offset doesn't happen at exactly the subplanetary point. Here, 0 and 1 is the subplanetary point, that if the system were transiting, and this particular planet is not transiting, but if it were transiting, that would be at the time of transit. And here the phase of greatest impact on the star is ahead of the subplanetary point. And so this is actually modeled and predicted to happen in multiple ways. There's actually multiple teams here, and I give you a list of references of people you can look, of papers you could look up. But here, this is just one example of the movie, showing you how you could see material and energy flowing from the planet onto the star ahead of it in its orbit, in part, especially if you have a spiraled stellar magnetic field lines, kind of akin to the Parker spiral that we see for the sun. And so this is one of the earlier ones, but there's lots of work and people are really motivated by understanding this magnetic interaction. So this is a paper from 2018, just showing a summary of the measurements of our hot Jupiters. And so we have the blue points here are for those planetary systems for which we see this magnetic interaction. Essentially, we see variability in the calcium H and K correlated with the planet's rotation period and not the stellar period. I'm showing you this night-to-night activity, essentially just of the calcium H and K. And on the x-axis is a quantity that we know the mass of the planet over the rotation and orbital period the rotation period of the planet and also its orbital period, because we expect these hot Jupiters to all be tidally locked at this distance to their planet star. And this is a quantity that is proportional to the planet's magnetic moment. Now, of course, you'll notice here that tau boo, we do detect variability with tau boo on the planet, on the star due to the planet. However, it's off this curve, so you might expect less of an interaction because this is the one system where the planet and the star are nearly tidally locked to each other. So the rotation period is very close to the orbital period. So for this one, it's a little bit more challenging to disentangle, but we saw already in photometric variability from space and so on that we have a consistent signature on the star that appears to be due to the planet. And so this is, in some cases, you might consider this the exception that proves the rule, right? Where you expect less interaction because they are tidally locked and the planet is not sweeping at very high velocities through the stellar magnetosphere. However, it's not always so simple, right? Nothing is ever quite as simple. We saw 2 out of the 8 epochs, 2 of the 8 out of the 8 times that we visited HD 1799, we saw spot modulation instead of orbital modulation. And so you could see here, this is the same curve, the model of our magnetic interaction with the planet. But then we come back in 2 epochs, back in 2003 and 2006, where it's not phased at all. But it seems to be very nicely phased with a rotation period of 7 days. Of course, there's offsets because we're not looking at the same stars or the same star spots and so on. So what this turns out to be interpreted as is a change in the interaction because there's actually a change in the stellar magnetic field, right? And this is true in our sun. The solar magnetic field configuration changes, as we know with solar cycle. And so we should expect that there should be dependencies on the changes of the stellar field independent of the planet's field. And this is an old paper, so pardon the low resolution. This is the highest quality image I have of this, but essentially what it's showing you is a simulation by Steve Cranmer and Steve Sarr that you could see that the calcium H and K variability as a function of in this case, using actual solar data, will change the signature. That in some cases, you'll see the solar rotation, and in some cases, you'll see measure the solar rotation, and in some cases, you'll see the stellar activity in there. And so that's something to keep in mind, because I'll talk a little bit later about how we measure magnetic field strengths on the stars and know that they do vary. All right, so this is kind of a natural place to pause for questions. If there are any, please raise your hand and ask them. I'm not following the chat if anyone else is.
I am raising my hand, but first I want to check, this is Pedro. I want to check if there are any other questions. I have a question myself.
Sure.
It's regarding tau boo.
Mhm.
You know, I like challenging, and I like these systems where the orbital period of the orbital period of the planet could be the same as the rotational period of the star. This is the case for tau b, and I can see that it falls away from this relation. But why is it still producing any interaction at all if it is synchronized? If the planet, the orbit of the planet is still synchronized with the rotation of the star, there wouldn't be any differential movement between the object orbiting the star and the magnetic field. So I don't understand too well why this happens. Yes,
that's a great question, because there is a dependence on the relative velocity. Well, it's not perfectly synchronized, first of all, so there is some relative velocity. The planet mass is very high. It's the highest of the system. So if the magnetic field does have a scaling with mass, you could expect that the field might be stronger. And also there's differential rotation on the star. So there are regions of the star that are not synchronized. I mean, the whole star isn't perfectly synchronized, but certainly there would be regions of the star that are most certainly not synchronized. So it is definitely more difficult to say conclusively, but it seems to be the case that the phasing continues year after year that we observed it, and included also there's photometric evidence of this from Walker et al. 2008, using the MOST spacecraft, where they see multiple years of spots synchronized with the planet's position. So if it was not at all synchronized with the planet's position, those spots should have evolved over time from year to year, right? We do know that there is spot evolution, right, on all stars. And so to have a consistent spot over many years would be very unusual, especially for an F star.
I see. And if I may have another go to ask you another question regarding HD 179949. Does the star have a magnetic cycle, a long-term magnetic cycle? Was it where in this magnetic cycle, if it does have one, where these observations that you showed, the first one and the second one, where in the second one you didn't get any detection, where were they placed in this phase?
So in my 2008 paper, we map the seasonal average activity, and you can see that it is varying on a long time scale, but we've never seen the full cycle. Like for the sun, it's 11 years. So we've never seen the full cycle. We could just see it monotonically increasing in activity. And I haven't been back to check where it's at. So we haven't seen a turnover or a change, or can give any constraint on the period of its cycle. But I in that paper, which should be able to say, I don't remember where it is, but it's just monotonically increasing. Now, where we have seen variability is in tau b, the one that you just mentioned. Tau b has shown a 2-year stellar cycle through Zeeman-Doppler imaging measurements. And so the star itself has a fairly weak magnetic field, but the polarity reversals have been detected multiple times, actually. So that's the only star of this sample for which that's been done. And it's very short. It's surprisingly short, right? It's 2 years as compared to our 22-year cycle on the sun.
There are stars that show these short magnetic cycles, particular M-dwarfs that are not, well, when they are close to the or beyond the boundary where they become fully convective, and this sometimes happens.
And they show short magnetic cycles?
Yeah, they can show short magnetic cycle, yes.
Oh, excellent.
Yeah. Okay, sorry. Yeah, but I don't have any other questions.
Okay, I see there's something in the chat. Let's see, is there any questions in the chat? Oh, someone agreeing.
Yeah.
Okay, perfect.
Okay.
All right, I will continue on. Thank you. All right, so let's talk a little bit about why we might expect to have measurable, i.e. stronger magnetic fields on these hot Jupiters than say for our own Jupiter. Here's one paper that came out from Yadav and Thorgren in 2017, where they say, well, because these Jupiters are so close to the star, to the central star, there actually also is this intense external heating that could drive stronger magnetic fields. And here, just to show you, here's a range of their predictions in mass. The color coding is in mass, and then size, and the magnetic fields here lie much stronger, right, between 50 and 200 Gauss in the dipole field, as compared to for our own Jupiter, which is 4.3 Gauss. So it stands to reason that it's possible that we could be measuring much more stronger fields. In addition, because the reason why this is important to understand the different physical mechanisms in hot Jupiters for the generation of fields is because in the early days, people really doubted if they could have strong fields at all, because they should be tidally locked and therefore relatively slowly rotating compared to our own Jupiter, which is a 10-hour rotation. These should have a multi-day rotation, and therefore initial ideas were that they would not have strong magnetic fields. Now, there's a bunch of theories in the literature right now. I'm just going to cover very briefly a couple of them and show why we're starting to consider that this flux tube scenario is in fact perhaps what is really happening. So here at the bottom is a flux tube scenario. There's a reconnection scenario here. These are proposed by Nuccio Lanza. And essentially he comes up with this scaling relationship here, where the SPI power, so SPI is short for star-planet interaction, the SPI power that we measure is roughly on the order of 10 to the 21 watts. So this excess heating due to the interaction with the planet comes out to be roughly 10 to the 21 watts for the systems for which we detected this. And he worked out that this power is proportional to the magnetic field strength of the star and the magnetic field strength of the planet and the relative velocity between the two at the location of the planet, right? And so if all these quantities are known, other than the field, we could use the measured power to solve for the planetary field. And that's the mechanism.
It's only me, or we lose Eugenia?
No, we have lost her.
Yes.
Yeah.
We lost the speaker, yes.
At the end, I also have a list of review papers that have even more references for you. So
Eugenia, sorry,
yes.
We lose you for 20 seconds.
Oh,
So maybe can you go back one slide?
I'm sorry. This slide?
Right, yes, from
Okay.
all known quantities, yeah.
Okay, so I'll just quickly repeat that that because of these large powers, relatively large powers, we can exclude the reconnection scenario, and the flux tube scenario can still work, and that's very helpful for us. And the idea here is that if we can measure the power through the data that we collect, and we can measure the stellar magnetic field through Zeeman-Doppler imaging, and we know the relative velocity between the two bodies, we can then solve for the magnetic field of the planet. That's how we do it. And I just wanted to also put these references here at the bottom, so people who are interested in following up this more deeply can. Also at the end, I have a list of very good of 3 review papers that also include all relevant references. Now, since we need to understand the magnetic field of the star, I wanted to briefly cover how people do this. We use Zeeman-Doppler imaging with a spectropolarimeter. The original work that produced the magnetic fields for the planets I'm going to talk about, where it was done with an instrument on the Canada-France-Hawaii telescope called Espadon, and it's a spectropolarimeter going all the way from the blue to the red part of the optical spectrum. Now the instrument is equipped with an infrared spectropolarimeter as well, so we can do this now on later type stars. I guess, Pedro, that's related to maybe that's the data you're referring to. is looking at magnetic field variability on late type stars. So essentially what you see is we're measuring the Stokes V in a star spot passing through the stellar disk, all measured within the photospheric absorption lines in the stellar spectrum. Okay, so it's analogous to normal Doppler imaging, as we've done it, as you probably know about, but now done in polarized light in Stokes V. And then once you have all the different kinds, different configurations, we can put it together and we can then model what the stellar magnetic field is at the location of the planet. So this is work done by Claire Matou and Rim Fares, and you can see that for this particular planet, Kepler 78b, how close it is probably to its magnetic field of the star, so that this field of the star is both measured and mapped. So you get you get the surface mapping as well as the strengths of these fields on large scale, the large scale structure of it. So this is a key ingredient into being able to pull out actual magnetic fields of planets. So now we have, of this scaling relation from Lanza et al., we have the power that we can measure from the observations that we've been doing from the ground. We have the stellar field also from the Zeeman-Doppler imaging, and we have the relative velocity, which we just know from the orbital properties of the planet and the stellar rotation, and we can pull out the magnetic fields. And so here's an example of more. Here's just showing more of these. These are the 4 systems that were published by Wilson Colley and myself and collaborators in Nature Astronomy in 2019. And why there are only 4 and not the full suite of them, of the 6 that we have, is because these are the ones we were able to do very good flux calibration. So flux calibration is notoriously challenging in high resolution shell spectroscopy. And so we were able to do it for these 4 systems only. Also, these 4 systems have, well, we can do it for all the systems that have, I should say, we can do this flux calibration for anything that's been done with this particular instrument, but these are also the 4 that have published magnetic field strengths, right? Because that's part of the equation. And what you see here is I'm just showing you the calcium variability going on here, and then the orbital phasing of each one. And similar to what I showed you with 17949, right, up here, where you have the phasing of the peak of the activity happening ahead of the subplanetary point, that remains true for all of these. They all go a little bit ahead of the planet, which is yet more confirmation that whatever is happening is probably physically similar. Now, I point out that there's a possible LOFAR detection right now in the literature for Tau Bu. So it is not yet confirmed, but it's exciting to see that people are starting to make observations of these hot Jupiters at radio frequencies, because the radio frequency will give us a confirmation and a calibration of our own deduced magnetic field strengths. So of these 4, here, what I'm doing is I am comparing our measurements for these 4 planets that are right here to those that using the same theory of Yadav and Fungren, and you can see that they do not a bad job. We only have 4, but they're in the same ballpark, right? This idea that they're between 20 and a couple hundred Gauss, that these are stronger field strengths than one might naively assume due to the slow rotation of the planet. So this is exciting. This is a really, I think, really fabulous to have this kind of agreement. We need more, of course, than 4. This is heavy duty work. We have another system right now that has a very nice period with the planet over multiple nights here. It has not yet been totally confirmed because this is only one run. I would like to do this again before we announce another magnetic field strength. Again, it's hard to get time to do this. So I know for those of you interested in doing this, getting the time cadence, right, with the multiple visits to cover both the rotation period and the orbital period is a challenge. And so we will continue banging away on this particular system, but also just keeping that in mind but it's important work. So I encourage those of you with access to a lot of monitoring time with high resolution spectroscopy to please continue doing this work. All right, so I'm going to pause. If there's any more questions, I do see something in the chat. Oh, okay, also agreement. So I'm glad, Pedro, you asked an important question. Are there any questions now?
Yeah, we have Miguel has raised his hand. Go ahead, yes, Miguel.
Very interesting stuff you are doing, Evgenia. So my question is actually a clarification. It happened with the reconnection when actually you had to reconnect yourself to the talk, and I think I missed the point. Why the reconnection can be ruled out? I mean, you mentioned that because of the large powers observed or needed. So do I understand correctly that reconnection doesn't provide these large fluxes? So what is the reason why the flux tube is, let's say, okay, and not the reconnection? Just a clarification for this.
Yes, you're absolutely correct. It's because, at least with the model that Nuccio Lanza proposed for the reconnection, we cannot reproduce 10 to the 21 watts. That's the main point. Okay. If there are other tweaks to the model or a different kind of reconnection model, then perhaps it is not fully ruled out, but that particular one can be.
Okay, fair enough. Thanks.
Okay.
Any other questions? Miguel, okay. I have one, Virginia. Claire and Rim are modeling this Zeeman-Doppler imaging.
Yes, they
are modeling.
Yes, they are collecting the data and applying existing models to interpret the Zeeman-Doppler imaging data in order to create the environment, the magnetic environment of the planet. Other people who are doing this, Jean-François Donati, if you know him, and Moira Jardine, she's very much involved in that work. Alini Vidotto also is also very much involved in taking these data and producing the magnetic environments.
These codes, are they valid for any type of stars or only for G stars? I mean, if we had to go to, if we wanted to go to M-dwarfs, would it be automatic that you could use them, or?
I expect they've been doing it already for M stars. I think they have been doing it for M stars. I don't know how much of the code they had to tweak to make it M-dwarf compatible, but I think they are definitely working on that. So I would encourage, I can connect you, I can encourage you to reach out to them.
Yeah, they are. Yeah, if I may comment, actually, I mean, on the work on Proxima and AU-MIC, they apply those codes using also this Zeeman-Doppler imaging. So yeah.
Okay, thanks.
Sure. Okay, where am I? I am here. Okay, so now that we've talked about what we're doing in the optical from the ground, just very briefly, we do eventually want to move this study into radio observations of these magnetic fields, because you could get from the frequency of the observation, you can get a more direct measure, not completely direct measurement of the magnetic field, but you get a more direct measurement of the magnetic field because the frequency scales with magnetic field strength. So the frequency of the radio emission specifically scales with magnetic field strength. And so that's very promising and hopeful. And also we could do this with, we're also hoping to do this in the UV by looking for aurorae, because we know that Jupiter has these beautiful UV aurorae, so does Saturn, and that is also a magnetic interaction with the sun. And so, so there are hopes to do that as well. Now, we have not yet done this, right? There are potentially some claims, but I don't think we have yet measured magnetic fields in exoplanets, unless you want to consider a planetary mass brown dwarf, which I would argue is potentially a first radio detection of an exoplanet. But again, the formation mechanism of the brown dwarfs and the exoplanets are different. And so this is an observation done by one of my team members, Melody Cow, who is now a postdoc at UC Santa Cruz. And she had observed a very strong magnetic field on a brown dwarf, a kilogauss field now, right? So 1,000, 500 to 1,000 times stronger than Jupiter's. So of course it's very different. It may be related to its formation mechanism, but the planetary mass for this object is about 6 Jupiter masses. And so maybe there's something we can learn about that. Here's a plot showing magnetic energy density as a function of energy flux. And what you see here is the Earth and the Jupiter lining up with where a lot of the other brown dwarf simulations are. Stars are way up here, kind of up here in this corner. The measurement that she has made of this planetary mass object is up here. And if you take our hot Jupiter measurements from our Kali et al. 2019 paper, these are the same four that I showed you earlier on this plot. And I mean, that's not bad. With only 4 points, it's lining up along this scaling relationship. So this is yet further evidence that that magnetic fields of hot Jupiters are stronger than our own Jupiters. So there are other possible magnetic events that have been reported in the literature. This is not a complete list, but there are searches for X-ray activity. So essentially the same idea, magnetic star-planet interactions as observed through increased stellar activity, but instead of calcium-2, they now use X-ray activity. And so here's a paper where they show phased X-ray activity with a hot Jupiter system. Here, there's also, I already mentioned, the Tau system might have a radio detection from Turner et al. 2021, yet to be confirmed. There was also a paper that came out from a LOFAR group saying that detecting radio emission from an M-dwarf, M4.5 dwarf, UJ1151, there's no confirmed planet around this star. So they're probably just seeing stellar flares because the only way to really confirm that this is truly star-planet interactions is to be able to match the radio emission to the orbital period of a planet that exists and that is known in the system. So I would not consider this yet to be a confirmed indication of a magnetic field on a planet detected, but certainly this is very exciting because this is we're going to learn a lot more about stars and the radio, and in order to do this. So the physics of flares and the physics of radio emission is going to be very interesting and something that's going to come out of this natural search. But also we're getting to the point where we're getting to the low frequencies to start measuring the field strengths, the kinds of field strengths that we're already observing in the optical. So again, this is expensive observations. They need extensive monitoring, but I think we can do it now, and we're getting the systems in place to do it. There's been another potential claim of a magnetic field through the bow shock method. And here people have observed in the ultraviolet a transit in the ultraviolet that may be a magnetic field induced bow shock. So this is other work. And with this kind of work, they are able to set an upper limit on the magnetic field of 24 Gauss for this particular planet, WASP-12b. So keep an eye out for that. I think as we get more and more UV transits, we can start looking for this. And I'll mention that briefly in what we're trying to do from space with a new mission. So ultimately, we have just the 4 right now. We definitely need more. And I encourage folks to keep working on it in this direction. One way that I've been trying to do this in the ultraviolet now specifically is with UV scope. This is a mid-X concept that we proposed to NASA. Now, the main goals of UV scope is to do spectroscopic characterization of the planets themselves. So it's a planet transiting mission, primarily to look at the upper atmospheres of the planets, to understand the planetary atmospheric escape through Lyman alpha, also characterize stellar environments. But through these data, we will also be able to look for these bow shocks, potentially look for aurorae. So even if not a driving science case, I think that there is potential with UV scope to study magnetic fields of these exoplanets. Now, again, it's just a concept right now. We won't find out if we've won or not until September. But it's an exciting system for many reasons, and that is an exciting mission, I think, for many reasons, not just for the magnetic fields. It will have a lot of capability that we so desperately need. So the idea briefly is that it's a 60-centimeter telescope, and it'll have 2 channels, a high resolution far UV channel and a low resolution near UV channel, but simultaneously. So we could get the entire stellar spectrum or planetary transit spectrum simultaneously. And this is something that's very difficult to do with HST, especially at the monitoring, right? So we talk about the need for monitoring so much, and getting the enough time on HST to keep doing this work is, of course, very hard when you have 100 programs a year competing for time. So let's talk about the what interests many people, including myself, is what about habitable zone planets around M stars? So I'm showing you the same picture. So this here is the same solar eclipse I showed earlier, but now instead of a hot Jupiter, I have put an Earth here in the corner at the location of Proxima b. So if you now imagine that this is not the sun, but this is in fact Proxima Centauri, and you've now reduced the radius right in your mind to Proxima Centauris, and you put Proxima b to scale, right? It's actually about 10 stellar radii away from Proxima b. So you're really now in this sub-alfvénic zone, possibly, for Proxima b in and around Proxima Centauri. And so you're now, what now is happening is that if you take this classic habitable zone plot, as you see here, we have mass of a star. Here's the Earth, right, at 1 AU. For Proxima Centauri, down here at a much lower mass, and you put an Earth-like planet in its habitable zone, you really are in what I earlier referred to in the SPI zone. So we really, I think, M-dwarfs are giving us an opportunity to look for magnetic fields on exoplanets that are very close. And then if you take the same scaling relationship that we've been using, where you can measure the power, you can measure the magnetic field strength of the star, which is already happening as we discussed earlier. We know the relative velocity, right? We could try and tease out the magnetic field of the planet, which for M stars, the B field is much stronger. So in principle, we could be sensitive, all else being equal, we could be sensitive to weaker magnetic fields of the planet for the same SPI power measurement, right? I mean, that sounds straightforward. Of course, nothing is so straightforward, especially for M stars, right? M stars have this complicated factor that they vary on much shorter timescales and with much larger variability because of intrinsic stellar activity, including flares. And this is just one example of a nearby star, Kapteyn star, that has a debate currently in the literature of whether or not it hosts a super Earth in the habitable zone or not. That's kind of independent of this talk, because really what I wanted to show you was looking at the this plot is showing calcium-2 measurements, the same that we are using for our hot Jupiters. And you can see that this variability is on order of, I don't know, 20, 50%, right? And if you remember back to our high signal to noise spectra, our SPI signals are 1 to 2%. So it's really going to be hard to dig out that kind of measurement. So if the SPI signal is much greater in M-dwarfs for some reason, perhaps due to the stronger stellar fields, maybe it's doable, but ultimately it's going to be harder to do this for M stars. Not impossible, I think, but it's going to need more data and more sensitive equipment because of course M stars are intrinsically fainter than these FGK stars that we've been observing thus far. But they're also slower rotators. Some of them are slower rotators, and so in this case, it would also take longer to be able to tease out what is really happening on the stellar period side versus the planet period side, but they're very distinct, right? So the planet orbital period, say for Proxima b, is 11 days, right? Whereas the star orbit, it rotates at about 80 days, similar to Kapteyn star. So this is, I think, a direction we should be going. It'll be very interesting, but again, we're going to have to collect enough data to tease out what the planet signal is from the stellar signal. So I think we're going back to this phase, right? We're going back to looking for planets in the radio. I think we're going to be capable of doing this, especially for M-star planets. What's exciting, though, about this is that I think because it's very hard to even get, it's harder to find the small planets around M stars because of the activity I just talked about. that as we get more and more radio arrays, sensitive radio arrays online, with this idea of all sky all the time, ton of monitoring, so much information, that maybe we will go back to this original vision of using radio observations in search of signatures, periodic signatures of exoplanets. So I think we're going to come back to this, and I'm very excited about seeing where that goes. It might actually be one of the best detection techniques for M-dwarf planets, especially around very active M stars. For those of you, I promised a list of review papers. Here are 3 papers where you could find all information, all the latest at all wavelengths and different models for magnetic star-planet interactions. And I just want to leave you with the idea that more exoplanet field detections are coming in different ways. And here's a list of ways that we and others are looking for them. So of course we want space-based monitoring, like for UV scope and other UV ways, and perhaps X-ray small satellites could also do this. I'm trying to still confirm that one that I showed you for our next hot Jupiter ground-based observation. There's a proposal to do spectropolarimetry of the helium-1 line to look for, in transiting planets, to look for magnetic fields there. Of course, as the ground-based observations, everyone is waiting for and excited to hear some confirmations from LOFAR. There's also a future space-based cluster of radio smallsats that people are thinking about in order to do these lower frequencies observations for planets like Earth. But of course, you have to be above the atmosphere at those particular frequencies. And there is a Pathfinder mission for this exact idea called Sunrise, which is looking at, it's going to be 6 CubeSats that work together to study the sun, but it is a Pathfinder for eventually building an array of radio smallsats to look at exoplanetary systems. And there's also a probe class sized concept called FarSide, where people are thinking about putting a radio array on the backside of the moon, where it's also relatively radio quiet, and we can look for very low frequency, high sensitivity observations of exoplanets. So I'll leave you with that, and I'll take any more questions if there are.
Thank you very much, Eugenia, for this wonderful talk. And Pedro, please manage for the question session.
Yeah, Miguel has a question for Eugenia.
Yeah, well, thanks a lot, Eugenia. Very nice talk, very useful. I just, well, for now, it's just a comment. We are also, as you probably know, we are pursuing this goal of detecting, star-planet interaction in M-dwarf stars. And actually, we tried with Proxima. We think we have found some evidence that is maybe to be confirmed yet, or to be unambiguously confirmed. But in 2021, we published monitoring with using the ATCA, the Australian Telescope Compact Array. Sorry for the sound.
Sorry for what? Oh, you cut off.
Oh, sorry. There was some noise here. So, okay. So my comment is that maybe we have already found this in Proxima B. Right. Only that apparently, when we used a model, a simple model taken from the sun. So basically, we thought we were in the sub-alfvénic regime. Now, latest results seem to suggest that this is not the case. So if it is not in sub-alfvénic regime, then this radio emission we are detecting, how in principle, which correlates with the orbital period of the Proxima B, may have a different origin, maybe if stellar flares, as this case of you mentioned of J1151. But otherwise, we are observing that Proxima B, Luis Peña Moñino, who is also in the talk, is actually reducing this data. And stay tuned, you may get some surprises.
Oh, wow, that's very exciting. I think if you find a modulation with the planet period, then that's more convincing than some of the sub-alfvénic measurements, because understanding where the Alfvén radius really is actually quite complicated in and of itself.
Yeah, exactly. Yeah, that's actually our, let's say, agnostic point of view. But theorists, say, oh well, it cannot be that. My model predicts is in the sub-alfvénic regime, you are wrong. That's, you know, that's normally you ask any of these models, they rucksack us based on these models. But you know, stay tuned for the new observations, and we will let you know.
I'm looking forward to them. Thank you for sharing.
Okay. I have put the link of this paper in the chat in case if anyone is interested. Any other questions?
I have another question, if I may.
Oh yeah, sure.
So, Evgeny, I'm not that I'm an expert on these UV observations, but could you then comment about this UV telescope? When will it be ready? Is there a room for collaboration, or which is the way this will be handled? Is that telescope thought, you know, for one group that will exploit the data, and when will be ready, basically, or available?
No. So the status is that we proposed it in December of 2021, and it's now under review with NASA. We will find out in September of 2022 if we've moved to the second stage. It's a two-stage process for the NASA mid-exes. And there is a guiding science program, right, to do exoplanetary transits and stellar characterization that will be executed in the first 3 years, but then the data, all the data, even of those first 3 years, become instantly public. For the most part, I mean, it has to go through some processing, but essentially the data will be public for everyone's use once it's cleared, of course, through the system. So it's not a proprietary data set at all. And then after the primary science is completed, then the mission, you know, presumably will become kind of a normal GEO program, guest observer program. That is yet to be determined what will really happen there. But we have a very specific, we have science cases already designed, I should say, but I think we can pull out data from those that are already planned, pull out searches for these kinds of magnetic fields from the same data set. So that's very exciting. So in the future, if it wins, absolutely there will be opportunities for collaborations. It would be a public facility through NASA.
Thanks a lot. Thanks a lot. Yeah, I look forward to it. Thanks.
Okay, that doesn't seem to be any more questions in the chat or any other raised hands. So, René, so yours again.
Yeah, thank you, Pedro. Thank you for all the participants, and thank you again, Eugenie, for this wonderful talk. And hope we can see in person here in Granada. And fine.
Great.
Thank you very much, Eugenia. That was very useful, very nice.
Thank you very much, Eugenia. Yeah.
Thank you. I hope to see you guys soon.
Yeah, I hope to see you too in person. Yeah, that would be great.
Take care. Bye, everyone.